Some of the concepts that I've mentioned in passing have been linear dependence and linear independence, and these are going to be the focus of this video. So let's begin with a definition. This definition is going to be familiar. A vector v in an abstract vector space, capital V, is a linear combination of vectors u1 through uk, also living in V, if v can be written as v equal to c1u1 plus c2u2, so on and so forth, out through ck for some scalars c1 through ck. This is exactly the way that we write linear combinations of vectors in Rn. It's essentially the same definition when you're talking about vectors in any type of vector space V. So for easy examples, 2, 2, 2 is a linear combination of 1, 1, 1 and 3, 3, 3 in the usual way. You can also write down examples of linear combinations of vectors in M2, 3. M2, 3, remember, is the vector space of 2 by 3 matrices. The matrix 1, 0, 1, 0, 1, 0 and the matrix 0, 1, 0, 1, 0, 1 can be added together and scalar multiplied with 2 and 3 in order to produce 2, 3, 2, 3, 2, 3. So this matrix is a linear combination of the other two. Now, going about finding the right linear combination that produces some desired vector is a classic problem that we know how to solve when we're dealing with vectors in Rn. Let me review that right now, even though we've discussed it before. So how do I find a linear combination of vectors in Rn? The short answer is you're going to use Gaussian elimination. So for example, what if we want to write the vector 1, 1, 1 as a linear combination of 1, 2, 3, 0, 1, 2, and minus 1, 0, 1. Let's call these vectors v and then u1, u2, u3. The idea is we want to know the three scalars that we need so that we can write the appropriate linear combination v equal to c1 u1 plus c2 u2 plus c3 u3. So the idea is you construct an augmented matrix and then you use elimination. What that looks like for this problem is not particularly long. Our augmented matrix has the vectors u1, u2, and u3, and then a dotted line followed with the vector v. We apply a series of 3 row operations to put it into reduced row echelon form, after which it looks like this. You can notice at this step that there are 2 what I want to call pivot columns. By that I mean these are columns that contain the pivots that we use to do the Gaussian elimination algorithm, and in the context of linear independence, which I haven't quite defined yet, these vectors are going to be independent of each other. Now for this particular problem, there are infinitely many solutions to the system, and there are infinitely many ways to write the linear combination that we seek. I know this at a glance because in my reduced row echelon form, I see a row that's entirely made out of zeros. There's only 2 pivot columns, but there's 1 dependent column, and that corresponds to the free variable that I'm going to have when I consider the associated system of equations. Let me think about this as a system for a moment to make it very clear. But this augmented matrix, rewritten as a system of equations using the reduced row echelon form of my matrix, gives me something that looks like c1 minus c3 equals 1, c2 plus 2c3 equals minus 1, and then my last equation is 0 equals 0. Notice here that c1 depends on c3 and c2 depends on c3, but c3 is free. C3 can be anything. So when I parameterize the solutions to my system of equations, I need to give C3 a name, and I'll call it t. T can take any value in the real line, and so C3 is t, C2 then becomes minus 2t minus 1, and C1 becomes t plus 1. So if I would like to write down a linear combination of the vectors u1, u2, and u3, giving me my vector v, which was 1, 1, 1, I can just pick t to be any number. If I choose t to be, say, 0, then I get the linear combination 1 times the vector 1, 2, 3, and minus 1 times the vector 0, 1, 2, no copies of the vector minus 1, 0, 1, which add up to give me 1, 1, 1. And of course, there are infinitely many linear combinations that I can write down. Here's another one. If I set t to be equal to 3, then I get a linear combination with coefficients minus 4, minus 7, and 3. So this process is really well established when you're dealing with vectors in Rn. Let's give another related definition now, and that's going to be the definition of a spanning set. So what a spanning set is a set S of vectors v1, v2 through vk that are a subset of a vector space V. So the set S is a spanning set if every vector in V can be written as a linear combination of vectors in S. And what we say is that this set S spans V. You think of these vectors V1 through Vk living in S as being the building blocks for the entire vector space V. So for example, if we are in R2, then 1, 0, and 0, 1 span R2. You can take any vector in R2 and write it as some linear combination of these two. 1, 0, 0, 0, 1, 0, and 0, 0, 1 similarly span R3. And if you take Rn, then the set of the what are called standard unit basis vectors, although I have not defined a basis yet, span Rn. And what these vectors are vectors that look like there's a 1 in the ith spot and zeros everywhere else. It should be fairly obvious that you can take any vector in Rn and write it as a linear combination of these. How about a different vector space? What if we take the space of polynomials of degree at most 2? In this case, the set consisting of 1, x, and x squared spans this vector space, which I'm denoting p less than or equal to 2. Let's see why. Well, if you just write down what a generic polynomial looks like, it should be fairly clear. A generic polynomial p is something of the form a plus bx plus cx squared. So what this is the scalar a times the vector 1 plus the scalar b times the vector x plus the scalar c times the vector x squared, all added up to give us this polynomial. By similar reasoning, you can see that this set consisting of 1, x, x squared, and so on and so forth out through x to the n spans the vector space consisting of polynomials of degree at most n. Let's now look at an example of vectors that span R3 and then vectors that do not span R3. So 3 vectors that do span R3 are the ones that I've written here, 1, 2, 3, 0, 1, 2, and minus 2, 0, 1. Whereas 3 vectors that do not span R3 are the 3 that I have written here. Now they look very similar, but notice that I've actually changed one of the entries. In the first set of vectors, this entry is a minus 2, and in the second set of vectors, this entry is a minus 1. And this makes a huge difference. So how can this be the case? Well, a geometric explanation for what's going on is that when you're dealing with vectors in R3, one vector will span a line. 2 vectors, if they aren't multiples of each other, will span a plane, and 3 what we call linearly independent vectors will span all of R3. But you can have 3 vectors that are not linearly independent, and in that case, they're only going to span together a line or a plane. The issue is how you choose to go about seeing that your vectors are linearly independent of each other. So there are lots of different ways to do this. In example 1, one thing we can do to quickly see that they're independent is to calculate the determinant of the matrix that's formed by stacking up these vectors as the columns. So I haven't mentioned this factoid before. This is the first time we're using it. But the vectors given here are independent because this matrix has non-zero determinant. The calculation of that determinant is worked out right here using cofactor expansion along the first row. So as we do cofactor expansion, what we see is we have a positive 1 times a smaller determinant plus a 0 times a smaller determinant, which is not indicated here on the page because the 0 doesn't matter, and then plus minus 2 times a smaller determinant. Each of those smaller determinants we can use the 2 by 2 formula for, and that gives us a determinant of minus 1, which crucially is not 0. This is not the only way to see that the vectors that made up the columns of this matrix were linearly independent. Alternatively, what you can do is take those 3 vectors, put them in the matrix, and then see that that matrix can be made into an identity matrix using row operations, so that when you put it in reduced or echelon form, you see the identity matrix. I have that sequence of row operations jotted down right here. I'm not going to work through all of them in real time, but if you'd like to check, there are a series of row operations that you can do to put this matrix into the form of the identity matrix. Because you've ended with something which is an identity matrix, that tells you that all 3 of those column vectors were linearly independent. And so we know that the 3 vectors in example 1 span all of R3. Now let's consider example 2. In fact, let's go through both of these methods for example 2. Let's calculate the determinant, and let's also analyze the matrix using row operations. We're going to need to go to the next page for this. So if we take the next set of 3 vectors, we're going to do the same thing in the sense that we put them into a matrix, and we're going to calculate the determinant of that matrix here. Again, let's do cofactor expansion along the top row. Now our calculation is going to give us 1 times a 2 by 2 determinant minus 1 times another 2 by 2 determinant. And as you can see, that calculation is going to work out to give us 0. From this calculation, we know that the set of vectors that we started with had some sort of linear dependence in them. They are not all 3 independent. In other words, there is a linear combination of 2 of the vectors that produces the 3rd vector. If all you need to know is whether those vectors were independent or not, then calculating the determinant is enough to say that. But it doesn't tell you exactly what that dependency is. It won't tell you whether all 3 of them were multiples of the same vector. So it won't tell you whether the set of 3 vectors spans, say, a line or a plane. If you want more information, you can use the matrix and perform row operations to put it into reduced row echelon form in order to see that. Why don't we carry that out right now? So we're going to take our matrix here, and we're going to start doing Gaussian elimination on it. All right, so from here, the first row operation that I want to do is I'm going to take minus 2 row 1 plus row 2. And after that, I'm actually going to do minus 3 row 1 plus row 3. These are not overlapping row operations, so I'm going to do both of them at the same time. The first row will remain unchanged. And in the second row, I'm going to have 0. I'm going to have 1. And then I'm going to have 2 plus 0, giving me a 2. In the last row, I'm going to have 0. I'm going to have a 2. And then I'm going to have 3 plus 1, giving me a 4. Next, what I'm going to do is take this 1 and use it to eliminate the 2 underneath. Before I was taking this 1, of course, and eliminating these entries. I follow this up with the row operation minus 2 row 2 plus row 3. Going into row 3. 1, 0, minus 1, 0, 1, 2 remain the same, and I get 0, 0, and then minus 2 times 2 is minus 4, so this also becomes a 0. All right, at this point, I'm actually in reduced row echelon form. I know that because not only do I have a triangular matrix, but all of the entries along this diagonal are 1, and I'm seeing zeros above and below them. But you'll notice these entries are non-zero. There's nothing I can do to get rid of them. And from here, it's very easy to see what the linear dependence amongst the columns is. When I look at this matrix, what I see is that column 3, the blue column, which is minus 1, 2, 0, can be written explicitly as a linear combination of the first 2 columns. So column 3, which is this, looks like minus 1 is a scalar times the column 1, 0, 0, plus 2 is a scalar times the column 0, 1, 0. That means that column 3 is minus 1 times column 1 plus 2 times column 2. I'm reading this right out of that matrix. Column 1 and column 2 are independent of each other. I'm staring at 2 vectors that cannot be written where one is a multiple of the other. There is no linear combination that relates them. But column 3 is dependent on column 1 and column 2. So out of this, I know that these 3 vectors together are going to span a plane in R3. So to summarize, in example number 1, the 3 vectors that we saw, which are on the previous page of these notes, spanned all of R3. But in example 2, we used row operations to reduce the matrix to a simpler form, from which it was revealed that column 3 was a linear combination of columns 1 and columns 2, but column 1 and column 2 were linearly independent. So that meant that those 3 vectors did not span all of R3. Instead, they spanned something 2-dimensional, a plane in R3. What plane was it? Well, it's the plane that is spanned by those original 2 column vectors, 1, 2, 3, and 0, 1, 2. One remark I want to make about this example is that we also checked the determinant as we went along because it's a useful trick. But this determinant trick only works when you're trying to check just whether n vectors in Rn span all of Rn. It doesn't tell you if some subset of them spans, say, a plane or something of smaller dimension. And in particular, this trick isn't going to work if you have something like 3 vectors in R7 and you're trying to determine whether they are independent. Because if you assemble those 3 vectors, you're not going to get a square matrix. So let's move on now. Let's write down another definition and a theorem.
For the definition, we're going to say that the span of a set is the set of all linear combinations of vectors from that set S. And notationally, we'll write span S. So S, you know, is a set of vectors, and think of them as building blocks. And anything that you can build out of those building blocks is in the span. And we refer to that whole set of possibilities as the span. In the previous example, we determined the dimensionality of the span of some sets of vectors. And so the theorem statement, to go along with this definition, is that whatever span of S is, it is a vector subspace of V. In fact, it's the smallest subspace that contains the set S. So in a previous lecture, we saw a lot of examples of things that were vector spaces and things that were not vector spaces. When you construct the span of a set of vectors that already belongs to a vector space, the question you would ask yourself is this a vector subspace? Meaning, does the set that I'm looking at have the property that it's closed under scalar multiplication and closed under vector addition, making it a bona fide vector subspace? And this is always going to be true if you're talking about the span, almost in a tautologous way. A standard example is going to be something like the span of 2 linearly independent vectors in R3, like what we saw before. And that's always going to give you some sort of claim that passes through the origin. So I won't prove this theorem here, but if you would like to do this as an exercise, what you would be doing is formally checking 3 things. You would want to show that the span of S is non-empty. You want to show that it's closed under vector addition, meaning you would take 2 vectors in span and make sure that their sum is in span. And you would want to show that it's closed under scalar multiplication.